To finish our notes on section 9.3, we're going to look at what happens if you're given a couple of the terms in the sequence and then you're writing the explicit rule on your own. We're also going to look at how you can set up approaching a word problem or a life application of these. So here's the idea for writing a rule for the nth terms. Whenever they say something like find the nth term, or if they just want you to write the explicit rule for an equation, the most important thing to keep straight is whether it's going to be an arithmetic or a geometric sequence, because that will change some of the instructions I'm giving you here. For example, whether you are subtracting the formulas from arithmetic sequence or dividing the formulas for geometric sequence. So they're going to give you two different terms in the sequence. It might be like the third and the eighth, whatever random numbers in the pattern they've given you. You need to set up two different explicit formulas, one for each of those given terms. Then, if it is an arithmetic sequence, so it's an adding pattern, you would cancel out the a sub 1 terms by using elimination, essentially, subtracting one formula from the other one. If it's a geometric sequence, then the way you're going to cancel the a sub 1s is by dividing the two equations. And then you can choose which one is on top and which one is on the bottom of the fraction. Try to just set it up so that the numbers work out easier, is my advice. After you've done that, you should either have a D or an R, depending on which kind of sequence you had, arithmetic or geometric. So solve for whichever variable you still have in the equation, D or R. And then once you've done that, you should be able to go ahead and fill in any of the missing values, because as soon as you know D, then you know what number to add to go from one term to the next. So you can fill in all the blanks. If you know what R is, then you can use that number to figure out what you're multiplying by to fill in the missing terms. And then you can find everything else you need to write the nth term equation in explicit form rule. So we'll do an example of each of those, arithmetic and geometric. So in this example, we're given the second and the seventh term of an arithmetic sequence, and those numbers are -1 and 24. So starting with the information we have here, if we are given the second term, that means n is equal to 2, and the number tied to that is a -1. So I can write an arithmetic sequence for this saying that a sub 2, which is -1, equals a sub 1, I don't know the first term in the pattern yet, plus n minus 1. Well, in this case, n is 2, so n minus 1 is just a 1. And I don't know the difference yet, so I'm just going to write d. Then I'm going to use the second set of information they gave me. They said we know the seventh term, so that would be n equals 7, and that seventh term is 24. So a sub 7 is 24. I still don't know the first term. And then n minus 1 is going to be 6 times the difference. I still don't know the difference either. So this is the setup I have right now. And then what I was telling you to do on the last slide was for an arithmetic sequence, you need to cancel the a sub 1s by subtracting one formula from the other. So I'm going to actually subtract this entire second equation from the first equation. The order you do the subtraction in really doesn't matter. The reason I'm doing the second one minus the first one is because then I'm going to end up with a positive 5d here. But it really doesn't matter if you do it with a negative. It just means you have a little bit more to do solving-wise. So 24 minus -1 will be 25. A sub 1 minus a sub 1. Don't forget you are subtracting this entire line. So it's a positive minus. We'll cancel out. And then 6d minus 1d would equal 5d. So we've just found that d is equal to 5. Now I know what the pattern is here. I know that the sequence of numbers is adding 5 over and over and over again. So I could go back to one of the earlier forms of the equation that I wrote and just plug in that d equals 5. Using that, I should be able to solve for a sub 1. Also, you can probably recognize that basically what we had was a blank, and then we knew the number -1, and then we didn't know the third, fourth, fifth, or sixth number, but now we know the seventh as well was 24. So now that I know d equals 5, you could also probably just kind of work backwards and say, well, then that means this number must have been -6, because they had to add 5 to this to get to here. But if you want, like I said, you can plug in d equals 5 into either of these two equations, and you should be able to solve for that the same way. So now I know a sub 1, that was one of the things they asked us to do, find the first term, and they want an explicit rule for the nth term. So for writing the explicit rule, that's where I leave things in terms of a sub n equals a sub 1 will be set. That number will not change from now on. now the first term of the pattern is always negative 6, plus n minus 1. I want to leave it in the nth term so that I can plug in whatever number for n that I need. And then the d value will not change. D is 5 in this case. And then if we did a little bit of distributing and cleaning up, I could distribute 5 times n and 5 times negative 1. So that would be plus 5n minus 5. And then I can combine the like terms and get that this is 5n minus 11. So those are both honestly good ways of writing your final answer, the first line that I wrote. But this one seems a little bit nicer and more condensed here. So now we're going to look at a geometric sequence example. It's going to be very similar. It's just going to change which operation we use once we have our two equations written. So I'm going to start off by saying if I know the third term, then that must mean n equals 3. I have 3 numbers. And that nth term is 6. So when I'm writing the geometric sequence formula, that would be a sub n, which in this case is 6, equals a sub 1 times r to the n minus 1 power. So n is 3. If you subtract 1 from that, it's going to be the second power. For the second formula I'm going to write, n equals 6, because it's the 6th term, and the number for that one is 162. So 162 equals the first term times r to the n minus 1 power. So this time it's the 5th power. Now, when I'm setting up my fraction on this one, I, again, would just recommend that you put one number on top or the other equation on the bottom to make it easier to compute. So I'm going to rewrite this as 162 equals a sub 1 times r to the 5th divided by a sub 1 times r squared. So now if we go to compute these values, I'll have 162 divided by 6, which is equal to 27. And on the right-hand side of the fraction, the a sub 1's will cancel, and r to the 5th divided by r squared, you just subtract the exponents, so that equals r cubed. And the opposite of the third power is the third root. So if you take the third root of both sides, you'll end up with r equals 3, because 3 times 3 times 3 equals 27. So now that I know the r value, again, I can take that value and plug it into either of the original equations that I had. I would probably recommend the one that has a smaller exponent. Or you could just try to set up that we know, we don't know the first term, we don't know the second term, but we know that the next term was 6. And you can kind of work backwards as far as divide by 3, divide by 3, divide by 3. But let me show you how to plug in r equals 3 and solve for this. So I'm going to take r equals 3 and plug it into this first equation that I have in red here. So that would be 6 equals a sub 1 times 9 from 3 squared. And then if I divide both sides by 9, I get 2/3 equals a sub 1. So now we have found the first term. We've also found the common ratio. That's the r value we found earlier, r equals 3. The last thing we need to do is write the explicit rule for the nth term. So for the explicit rule, it's a sub n equals, and then you plug in the a sub 1 value. That's something that's set and won't change from one solution to the next. So I'm going to write 2/3 times r raised to the n minus 1 power. And then there's not much simplifying you're going to be able to do on that example, so you can just leave it in that state. So next, I'm just trying to give you some advice on how to apply sequences to different word problems. Again, your solutions will vary from one question to the next, though, so there's no one set formula I can give you that will always take care of this for you. So the tips I'm trying to give you are to look for a number that describes the object either today or as some kind of a first count of something, maybe on the beginning, anything along those lines, and then that should be your a sub 1 value. So maybe they're saying how much money you had in the bank account at the beginning, for example. Then you're going to determine whether the pattern appears to be adding a certain number or multiplying a number. So a lot of investments are usually geometric because it's doing something like multiplying by 1.07 to show 7% growth. So it's multiplying by 1.07 over and over and over again. It could be something like a tree getting taller, in which case maybe it's always growing 2 inches per year. So every year it's adding the same amount. The number's not going to change from one to the next. So that would be an arithmetic. So you need to be able to figure out just from the pattern, are they adding numbers or are they multiplying your numbers by something? And then the last thing is to actually figure out what that rate is. Do they say that it's growing 2 inches a year? Well, then that would mean D equals 2. Do they say that the interest rate is growing by 7%? Well, that would mean R equals 1.07. So you have to be able to identify some of those variables. I recommend just labeling as much as you can and then plugging them into the formula to solve for what's missing. So here's a quick example. If you've seen the Harry Potter movies, there's the Gemino curse, which is used in Gringotts Wizarding Bank. So basically they're in there trying to get the Horcrux and they touch this item and all of a sudden the item starts doubling itself over and over and over and over again. So we want to figure out how many of those duplicates are in the vault after a mere 45 seconds. We could do it for a minute, 2 minutes, whatever. So the first thing we're going to do is try to label some of the values that are given to us. I see right here that they say there is only one goblet in the vault at the start. So that would be what you're looking for as far as a starting value. So I'm going to say a sub 1 is equal to 1. Now, the fact that this object doubles itself means that it's a geometric sequence, and specifically doubling, we use that to say that you're multiplying something by 2. So now I know that the R value equals 2. Now, the trickiest thing for us to figure out is the N value in this case. So they want us to find out how many there will be 45 seconds after the object is touched. And the doubling happens every 3 seconds. So your instinct is probably to say, okay, well, let's do 45 divided by 3. And that's good. That gives you a number 15. But that's not actually N. Because if you think about things for a second, for example, let's say we were starting off with 1, and then it doubled, so then you have 2, and then it doubled again, so you have 4, and then it doubled again, so you have 8, and it's going to keep doing something like that. Well, pretend that this had instead said 6 seconds later. This is how many you would have at 0 seconds. This is how many you would have at 3 seconds. This is how many you would have at 6 seconds. So if you do 6 divided by 3, you would have gotten 2 for an answer. But you can see that I actually have 3 numbers written out. What's happening is that by doing 45 divided by 3, we counted how many times we doubled the number of goblets. But that doesn't consider the starting number of goblets we had. It only counted how many times we did that multiplying process. So my N value is actually going to be that 15 plus 1. I actually have 16 numbers. We're doubling the number 15 times. That's what we found. But we have 16 numbers, and that's what N cares about. How many numbers do you have, not how many times did you double. So now that I have this information listed, we should be able to plug this into the geometric sequence formula. So A sub 16, the 16th number in the pattern, will equal A sub 1 times R to the N minus 1 power. So since N was 16, you subtract 1 from that, and you get 15. Now, the 1 times doesn't affect anything. All you actually have to compute is what is 2 to the 15th power, and that's going to give you 32,768, which is exactly why Harry, Hermione, and Ron were in so much trouble. It's because even in such a short time frame of 45 seconds, there are already 32,000 of those objects going to be crowding them into that locked vault. So that's all for the notes today. Thank you for your time.